Lecture 4.5, Linear Approximations, Differentials, and Newton's Method. This is Palouse Falls in the state of Washington. And this is looking downstream from the falls down the Palouse River towards where the Palouse River opens into the Snake River. Isaac Newton shares credit with Gottfried Leibniz as the developer of calculus. Today we will look at Newton's method for approximating the roots of a function. For any function f of x, the tangent is a close approximation of the function for some small distance from the tangent point. Here we see if we're close to the tangent point, the red line, which is the tangent, and the blue curve are approximately the same. We call the equation of the tangent the linearization of the function. Start with a point-slope equation, y minus y1 equals m times x minus x1. We let x1 equal a, y1 equals f of a, and m, which is the slope, equal the first derivative, f prime of a. Now the equation becomes y minus f of a equals f prime of a times x minus a. If we add f of a to both sides, we get y equals f of a plus f prime of a times x minus a. This is the linearization formula. L of x equals f of a plus f prime of a times x minus a. We call this the linearization of f at a. F of x is approximately equal to L of x is the standard linear approximation of f at a. The linearization is the equation of the tangent line, and you can use the old formulas if you like. Here are some important linearizations for x near 0. If f of x is 1 plus x to the k, then L of x is 1 plus kx. For example, if we start with radical 1 plus x, that's equal to 1 plus x raised to the 1/2, which is approximately equal to 1 plus 1/2 x. This formula also leads to nonlinear approximations. We could write the cube root of 1 plus 5x to the 4th equals 1 plus 5x to the 4th to the 1/3 equals 1 plus 1/3 times 5x to the 4th, or 1 plus 5/3 x to the 4th. Sin x is equal to y equals x when x is near 0. Cosine x is approximately equal to 1 when x is near 0. And tangent x is approximately equal to x when x is near 0. Differentials. When we first started to talk about derivatives, we said that delta y over delta x becomes dy over dx when the change in x and change in y become very small. dy can be considered a very small change in y, and dx can be considered a very small change in x. Let y equal f of x be a differentiable function. The differential dx is an independent variable. The differential dy is dy equals f prime x dx. Example, consider a circle of radius 10. If the radius increases by 0.1, approximately how much will the area change? We start with the equation a equals pi r squared, which relates the radius to the area. We take the derivative of both sides with respect to x, and this is one of those times when we consider the derivative to be a division, so we can multiply both sides by dx. This gives us dA equals 2 pi r dr, where dA is a very small change in a, and dr is a very small change in r. Now in our problem, we had a reasonably small change in r, although still not very, very small, but we are going to use 0.1 as our very small change in r, and we'll use 10 as our radius. If we plug those numbers into our expression for dA, we get dA equals 2 pi, which is the approximate change in area. Now we compare this to the actual change. The new area is pi times 10.1 squared, or 102.01 pi. The old area is pi times 10 squared, or 100 pi. The difference is 2.01 pi. So if we compare the error to the actual answer, it would be 0.01 pi over 2.01 pi, or 0.0049751. That is less than 0.5% error. If we compare the error to the original area, it's 0.01 pi over 100 pi, or 0.0001, which is approximately 0.01%. Now, even though this is a very small error, it is still an error, and you might wonder, why don't we just calculate the exact change? Well, we will have a use for this. You're just going to have to trust me on this one for a while. Newton's method, finding a root for f of x equals 1/2 x squared minus 3. We'll use this as our example. We will use Newton's method to find the root between 2 and 3. So I zoom in, and I have f of x equals 1/2 x squared minus 3, and I find the first derivative, f prime x equals x. Now I'm going to guess what the root is, and I'm going to make a spectacularly bad guess. I'm going to guess the line crosses at 3. Now we can look at this graph and see it doesn't cross at 3, but this will make it easier to illustrate the process and show you how powerful the method is. F of 3 equals 1/2 times 3 squared minus 3, or 1.5. What we're looking for is the value of the function to be 0. So we didn't guess so well, but we can look at 1.5 on our graph and construct a tangent at that point. The slope of the tangent is f prime of 3, or 3. Now, if we mark the distance from the tangent line to the 3 as z, and construct a vertical side to make the triangle, we see that 3, which is the slope, is change in y over change in x, or 1.5 over z. So z must be 1.5 over 3. So we can locate this point by taking 3 minus 1.5 over 3, or 2.5. And I have not drawn this to scale because I needed room to show you the next step. So now I have a new guess, 2.5. So now my new guess is 2.5. F of 2.5 equals 1/2 times 2.5 squared minus 3, or 0.125. So I construct a vertical line and a new tangent. And notice my drawing is not drawn to scale. The slope of the tangent is f prime 2.5 equals 2.5. Solving the slope equation for z, I get z equals 0.125 over 2.5. So my new guess is 2.5 minus 0.125 over 2.5, or 2.45. So I try the new guess. F of 2.45 is 0.00125, which is getting very close to 0. The slope of this tangent, f prime of 2.45, is 2.45. Solving for a little tiny z value, which you can just barely see in the picture, I get z equals 0.00125 over 2.45. And now I can calculate a new value, or a new guess. Now we take this guess and put it into our original function. And our answer becomes 0.000000130016, which is amazingly close to 0. Now, of course, we used our calculator, but given enough time, this problem could have been worked by hand, which is what you would have needed to do before the invention of the calculator or computer. This is Newton's method of finding roots. It is an example of an algorithm that is a specific set of computational steps. This is a recursive algorithm because a set of steps are repeated with the previous answer put in the next repetition. Each repetition is called an iteration. So this is the formula for Newton's method. X sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So we find the next guess, or next value of x, by plugging in the current value of x and the y value, or f of x sub n, and the derivative, which was the slope. This technique is sometimes called the Newton-Raphson method. Actually, the techniques that we will see in the next slides were developed by an English mathematician named Joseph Raphson and published in the year 1690. Isaac Newton developed a similar formula in 1671, but it was not published until 1736 and is not as easy to use as Raphson's method. Very little is known about Joseph Raphson, who lived approximately 1648 to 1715. He was acquainted with Newton, so he may have gotten the idea from Newton. Anyway, Newton tends to get the credit. No portrait exists of Joseph Raphson. We do have this bond he signed when admitted to the British Royal Society while still a student in Cambridge College. This bond is essentially a promise to pay his dues to the organization. So we have his signature at the bottom. One thing I find fascinating about this is his quarterly payments were all due on religious holidays, starting with the Feast of the Nativity. His first payment was due the 25th of December, which of course was Christmas Day. Nowadays, we don't make contracts with payments due on religious holidays. Example, find where y equals x cubed minus x crosses y equals 1. So this is the equation that we want to solve. 1 equals x cubed minus x. If we subtract 1, we get 0 equals x cubed minus x minus 1, which we can write as a function f of x equals x cubed minus x minus 1. And the derivative of that function is f prime x equals 3x squared minus 1. To use Newton's method, we're going to construct a table. First, after 0 iterations, x is our first guess, and I'm going to guess 1. F of x sub n is negative 1, and I got that by putting 1 into the f of x equation. F prime of x sub n is 2, and I get that by putting 1 into the f prime equation. And I then plug in x sub n, f of x sub n, and f prime of x sub n into the Newton's method equation, and I get 1.5. 1.5 then is my new guess after 1 iteration. I put that number into the equation for f of x and get 0.875. I put 1.5 into the f prime equation to get 5.75. And then I plug those three values into the Newton's method equation to get my next guess, 1.3478261. Obviously, I'm using a calculator here, but if you had just a little time, you could do it by hand. So after 2 iterations, this is my guess, 1.34 something. I can plug that value into my original equation and my first derivative equation. And then I use the Newton's method equation to get a new guess for x. If I try that back into my original equation, I see that my answer comes very close to 1. When we do these problems on tests, for example, I'm only going to ask for 1 or 2 iterations, just enough so that you can show me that you know what you're doing. There are some limitations to Newton's method. For example, We could be looking for this root, but if we make a bad guess, Newton's method could find a different root. So that's finding the wrong root. Another possibility, which usually occurs when there's an inflection point, is Newton's method might not converge at all. That's failure to converge. This is a statue of Isaac Newton as a college student in Trinity College Chapel at Cambridge University, Cambridge, England. We learn Newton's method of finding roots for historical interest and to deepen our appreciation of calculus. Newton's method is sometimes tested on the AP exam and will therefore sometimes appear on a test in this class. There are much easier methods of finding roots using our calculator. Example, approximate the positive root of f of x equals x to the fourth minus x minus 1. If you have the function graphed, you can find the roots by using F5 math 2 0. 0 is another word for root. Use the arrow keys to select the lower and upper bounds and press enter each time. And the calculator will find the root. You will need to find each root separately. An even quicker way to find roots is to use the following when in the home screen. F2 algebra, 4 zeros, and we enter this command, zeros, x to the fourth minus x minus 1, comma x. Press enter, and the calculator just tells us the roots.